Hello everyone. So today we are going to talk about some reactivity testing of supplementary cementitious materials. And I think many of you have been heard of the R3 test and maybe the modified R3 test. And today I'm going to introduce a new method developed in our lab that is called UR2 method. Those like R3 test, they take about 7 days or 3 days to get the results, while our UR2 method, it take about 5 minutes to get the results. So first, a bit about background. As many of you may know, the supply of traditional SCM like fly ash is becoming limited, and people have compared the availability of different sources and conclude that the natural clay minerals may be the only option that fit the future demand of SCM. And also, these clays are further developed into the LC3, limestone calcined clay concrete. They are able to replace about 50% of the cement and decrease the carbon footprint by 40%. So consider this availability and also its sustainability. Calcined clays are considered as one of the promising future SCM. But the problem is that these natural clay minerals, they are crystalline phase, so we have to calcine them, like activate them at several hundred degrees C, and then this crystalline mineral will become amorphous material, which will gain the proper reactivity as an SCM. But if we overheat them at a higher temperature, then these amorphous material will recrystallize and lose their reactivity. Therefore, when we produce calcined clay, the production condition is very important. And after the production, we need some methods to evaluate its reactivity, whether it's usable or not in concrete. So the most widely used method is strength activity index. This uses calcined clay to cast some mortar and test the strength after 28 days. And for a faster method, the R3 test is developed. It monitors the heat generation during the reaction of calcined clay, and it takes up to 7 days to get the results. And people found that this 7-day heat, it correlates well with the 28-day strength. They get R squared around 0.8. But the problem is that for all of these methods, it takes at least several days to get the results. During our production, we cannot keep using a wrong production condition for like a whole week. Therefore, we need to develop some real-time quality control techniques at the calcination plants. And currently, we don't have such a proper method. Therefore, the goal of this study is to develop such an ultra-rapid test. So we first select 3 different types of clay minerals, kaolinite, cementite, and illite. We calcine them at a different temperature and conducted the standard 7-day R3 test. The heat generation shows their reactivity. We can see that their reactivity vary widely among different mineral phases, and also their optimal production conditions are quite different. While in industry, the real clay minerals, they may contain a mixture of different clay mineral phases and other non-clay phases. Therefore, we cannot estimate the optimal production condition based on the experience. We need to develop a reactivity test. And we also look at the kinetics of this R3 test. For some of the minerals like kaolinite, their heat will generate very fast within the first 1 or 2 days. But for other clays like cementite and illite, their reaction become slower and slower. That even after 7 days, the reactions are still ongoing. Therefore, for this method, you really need to run for 7 days. And we also see some of the crossover of those curves. And for the ultra-rapid method that we are going to develop is based on the dissolution of the clays. For example, we dissolve these clays in diluted alkaline solutions, and we monitor the release of silicon concentration over the first 15 minutes of dissolution. We can see that only those kaolinite that calcined at proper temperatures, they will have very high concentration of silicon released. And also the reaction rate is also very fast. Similarly, for those cementite, we have a little bit lower concentration and a little bit lower release rate. And for illite, its concentration is the lowest, and also its kinetics is also the lowest. These are all consistent with the trend of their reactivity. And we can also see similarly those crossover of these curves. That said, the trend of the dissolution, it matches well with the R3 test. It's just whether they can be quantitatively correlated to each other so that we can use the dissolution to predict the results of R3 tests. So, for example, we do a linear regression between the silicon concentration released within 5 minutes with the R3 results. And we can see that there are some problems for those moderately reacted clays. Those are the cementite. We think it's because in cementite we have more silicon compared to aluminum, while for other clays they may have different ratio of silicon to aluminum. Therefore, we also want to consider the aluminum. But if we only use aluminum, we similarly will have a problem with those cementite. And we can combine silicon and aluminum together by adding their concentration up. But the problem is we are predicting the heat generation, so we want to consider what is the relative contribution of aluminum and silicon to the heat. Therefore, we checked some database, and we learned that the aluminum releases about 50% more heat compared to silicon. Therefore, we developed such a dissolution index. And using this dissolution index, we get the best correlation. And now those cementite are completely on the line of regression. But all of these clay samples we prepared using the relatively pure kaolinite, cementite, and illite. Therefore, we want to check whether they are applicable to a more realistic samples. So we collect 10 commercial calcined clays and 17 natural clays that we calcined ourselves in the lab. So totally we have 27 industrial clays shown in these red squares. Mostly this method still works, but with larger deviations. Especially some of the samples, we have more dissolution compared to the heat generation. We suppose this is because we are using relatively high temperature for the dissolution. Therefore, some of the crystalline impurities like quartz, they may also have a little contribution to the dissolution. And what we get is the sum of the dissolution of amorphous and crystalline phase. To separate the effect of those crystalline impurities, we also dissolve the sample before the calcination. And then we subtract their dissolution from the original results. In this way, we can get the dissolution of those amorphous material, which are the ASTM that we want to test. With this adjustment, we get a 5-minute adjusted dissolution index, and we similarly do a linear regression for all the 47 samples that we have. And now we are able to improve the R-squared to about 0.92. So in this way, we can use something that can be measured within 5 minutes to accurately predict the results of the standard 7-day method. We suppose that this can be deployed as a real-time quality control method at the calcination plant, that when the clay coming out from the calciner, we can continuously take a sample on the conveyor belt every 5 minutes and conduct our test. This test will monitor the performance of this material in the real time, and which will also provide a feedback to help us adjust the production condition to ensure the consistency in the quality of the product. So as a summary, we have developed a UR2 method that is able to predict the reactivity of calcined clays within 5 minutes. And for a wide range of different samples, we get a highly consistent results with the industrial standard methods. So this UR2 method have the possibility to be deployed as a real-time quality control method. It can help us save more fuels and also save more materials by avoid over-calcination. And it also ensures the consistency in the quality of the product. This can help the deployment of this new sustainable SCM in the cement industry. And finally, there are many people asking us whether these methods are applicable to other SCM. So we also test other traditional SCM like fly ash. We test 37 different Class C and F fly ash. And we see that similarly, this method also applicable to the other SCM. So finally, this project is supported by the ARPA-E and NSF, and we are from the UIUC, and here is a link for our group for you to learn more about other ongoing projects in our group. And that's all. Thank you for your time and listening.